Hey, what's up, guys? In this video, I'm going to be talking about Bose-Einstein condensation. I know that this is a little bit out of the context of physics news explained kind of video series, but I noticed that in a lot of news that breaks out, the concept of Bose-Einstein condensation is kind of key to understand what the scientists are doing in that discovery. So I thought it would be useful to have a video or two at least about Bose-Einstein condensation. So without further ado, let's jump in. So like any other video, I would like to start with basically defining what the concept is, and in this case, a Bose-Einstein condensate is basically a cloud of really, really cold gas, right? So at room temperature, right, molecules and atoms move around at really high speeds. They bounce off each other. They bounce off the walls, going randomly everywhere. They pretty much act like, billiard balls. So if you reduce the temperature, and by reducing the temperature, I don't mean by a little bit. Reducing the temperature, I mean reducing the temperature by a whole lot, pretty much close to absolute zero Kelvin. So at temperatures close to absolute zero, here in this case 100 microkelvin, which is 10 to the minus 4 Kelvin, which is really, really close to absolute zero, right? 0 Kelvin. You start to see some quantum mechanical effects. And this lambda dB is the de Broglie wavelength, right? At room temperature, about 300 Kelvin, this de Broglie wavelength is really, really small. So there's no way you can see any quantum mechanical effects, at least in a macroscopic way. But as you keep, reducing the temperature in this gas, you start to notice some quantum mechanical effects. In this case, at around 100 microkelvin, the de Broglie wavelength of the gas molecules start to become noticeable. But still, at this point, you don't see quite significant quantum mechanical effects. Then if you keep cooling down a gas up to down to 1 microkelvin, then that's where the de Broglie wavelength of these molecules become. At this point, I probably better use atoms. I know that I started with air, and air has molecules, right? But for my purpose, I would like to use term atom, because the gas, the Bose-Einstein condensate that we work with, is made out of atoms and not molecules. So I'm gonna switch to atoms from now on. So if you cool down gas of the atom gas down to 1 microkelvin, then the de Broglie wavelength of the atoms start to become noticeable and start to become basically almost the size of your system, right? So if your system is this big, then the wavelength of these atoms become almost the same size of your system. So if you keep going down in temperature, that's when every single atom, the wavelength is so extended that basically it's confined by the size of the system, and every single atom in that system will have the same wave function, which is kind of shown here, right? This kind of inverse parabola kind of shape, right? Versus up here, you still have some energetic atoms with a shorter wavelength, moving around and keep warming up your condensate. So by the way, this inverse parabola here is part condensate of your system, and you have some thermal atoms around the condensate. And as I said, if you keep cooling down a gas, eventually every single atom will fall into the ground state of the system, and they will all share the same wavelength. It's kind of an interesting analogy. They start basically dancing together. All these atoms, they follow the same wave function, right? If it makes sense. All right. So the actual conditions to form a Bose-Einstein condensate is a little more complicated than what we just talked about. It's all about the phase space density. If you have enough atoms, if you can squeeze them to a small enough phase space, that's when you will start to have a Bose-Einstein condensate, and there's a threshold for that, um, and so on and so forth. I don't want to get into too much details in that. Oh, by the way, before I go ahead, here's a real image of a Bose-Einstein condensate, and these sevens, these numbers are basically microns, like micro symbol, and I don't know why they're replaced by number 7. That's interesting. Anyway, so this axis is the units are micrometers, the same as the x-axis, right? So this condensate is extended about 100 microns, so 1/10 of a millimeter, right, across the x-axis, and about 20 microns along the y-axis. So along the x-axis, it's actually quite extended, and if you could somehow squeeze yourself into the apparatus that makes the BECs, you should be able to actually see the condensate. If it was if it was an object that could interact with light. To be honest with you, yes, Bose-Einstein condensates can interact with light, but as soon as you shine light on them, a kind of light that makes them visible to you, you start to heat up the system, and it basically is destroyed, right? Observing the system kind of destroys the system. It's kind of a heart of the quantum mechanics, right? All right, anyways, let's move on. So the question is, how do we cool down these atoms to such extremely cold temperatures? So we do it in 2 steps, right? Step 1 is called a magneto-optical trap. The way basically you cool down your atoms using a magneto-optical trap is that you shine 6 counter-propagating laser beams that are nearly resonant to the atoms. And the way you can imagine this is that, say here's a laser light, going that way, and an atom is trying to move that way, right? Kind of counter the way that the laser is shining. And as it's doing so, it goes into resonance with this laser beam and starts scattering photons from this laser beam and slows down, right? The way you can think of this, a cool analogy for this is, say there's a truck coming towards you and you have millions of tennis balls, and you can throw these tennis balls at the truck at a very amazing rate. So eventually, after about 40,000 tennis balls, right, you should be able to stop this truck, right? Actually, I was wrong. So the number that I was looking at, sorry, you need about 40,000 photons per atom to cool them down, right? But in terms of a truck, I haven't done a calculation. It's actually a cool calculation. If one of the viewers can basically do a simple estimation of that, that would be really cool. And I'm actually curious to see how does that number compare to our 40,000 photons per atoms, right? All right. So after throwing 40,000 photons at an atom, then the temperature of that atom will basically, well, talking about a temperature of a single atom is not right. So essentially, the velocity of that atom becomes so small that if you could convert that to a amount of temperature energy, that would be close to 100 microkelvin. So pretty cold, right? All right, but at this stage, this temperature is not cold enough for a BEC to form, right? So you need a second stage, like what I mentioned before. The second stage is called evaporative cooling, right? It works the same way as the way you cool down your cup of coffee. You basically blow air over the coffee, and you basically get rid of the hot atoms from the top of the coffee, and you end up with a cooler coffee, right? So it works the same way here. Say you have a container, you have a trap. It can We usually use the term trap for for trapping ions or atoms. Um, so you have a trap that contains all these atoms. The ones that are on the top are like the warm ones, the hot ones, if you will, and then on the bottom you have like the cold atoms, right? So you want to somehow get rid of these warm atoms. How do you do that? So you blow instead of blowing air, because everything you can't blow air atoms here, right? They're basically in vacuum, ultra high vacuum, and you can't do anything to ultra high vacuum because you can easily disturb it. Um, so anyways, so you blow some RF or radio waves at this trap in such a way that some of these warm atoms, right, become resonant with that radio frequency, and that radio frequency will basically flip their internal state, the internal state of those atoms. And so these atoms have three internal states, right? Say -1, 0, and 1, right? And only the atom state -1 is trappable, right? 0 and 1 basically cannot be trapped. So basically, the trap or the container is completely invisible to these atom states 0 and +1, right? So when you blow some of these atoms with the radio frequency, you can flip their internal state, and they will no longer be trapped, right? And the question is, how do you selectively interact with atoms with that RF radio frequency? It's very tricky. So you have a magnetic field in this trap, right? And these warm atoms, these hot atoms, basically move to the outer extent of the trap, right? And at those places, the magnetic field is stronger, and therefore the magnetic field basically changes the state of the atom in such a way that they can interact with this RF. And as soon as they interact with this RF, their internal state is changed, and then they will no longer be trapped. It's a very, very smart way of trapping atoms. And actually, this is the method that this was the key method that led to a Nobel Prize. All right, cool. So these are the two stages of cooling the atoms, right? So here in this picture, I want to show you a schematic of a setup that a typical Bose-Einstein condensation apparatus, right? So here's the first stage of cooling, right? The magneto-optical trap, in short MOT. And on the left-hand side, that's like that center, that's where you do your evaporative cooling, right? Look at all these coils. These black things are coils, and basically these coils do the job of evaporative cooling in simple terms, right? And these beams, these basically shapes that you see, these colorful shapes that you see, are laser beams that after basically you form the Bose-Einstein condensate, you want to manipulate the BEC using these beams and do your experiments, right? Obviously, the experiment, it's not just building the BEC. You want to build a BEC and start doing experiments on it, right? All right, cool. So let me see if I can explain a little bit more here. Well, probably it's easier if you see the actual thing, so I'm gonna jump right on. So this guy, right? So the MOT, magneto-optical trap, in real life, it looks like this. So you have a couple of coils, right? These coils are called basically some shim coils that you can bias your magnetic field a little bit. And so basically there's that, I don't know if you see the glass, that's the vacuum, right? That's a vacuum chamber. And in the middle of these two coils, that's where you actually generate your MOT, collect your atoms, right? So, like I said, the temperature of the cloud is about hundreds of microkelvin, and it's not a BEC yet. And a cool fact about a MOT is that if you're lucky, if you turn off the light and you look closely to the center of the trap, you can actually see the atoms. And this is true about rubidium-87 atoms in particular, because I've seen them, and I'm sure that you can see them if you look carefully enough. Because the resonant light with rubidium atoms is about 780 nanometers, and that's kind of far to the end of the red spectrum and into the IR, but you can still see those photons. It's pretty cool, actually. It's a really thrilling feeling that you're actually seeing a cloud of atoms suspended in the middle of a vacuum. It's pretty cool. Anyways, so this left picture here is the trap on this side. The one that does the evaporative cooling, right? We call it a magnetic trap. So notice this coil is basically similar to this coil up here. And what happens is that once you generate the mots, you basically grab them using these two coils and move them all the way from the mot, which is down here, to the magnetic trap where you actually do the evaporative cooling, right? And look at all these, complicated coils that do an awesome job of holding the cloud and cooling them down. Okay, so in real life, I want to show you how it looks like. So I have a video. Oh no, the video doesn't work. So at the end of this video, I'm going to basically show you the video. That sucks. Let me see if I can actually pause and bring up the video. One sec. All right, guys, I could finally find that video and attached it here to my presentation. And all right, so let's see if we can play it. This is the MOT, right? We're loading some atoms. The blue light helps with collecting more atoms. All right, transfer. Grabbing those atoms, dumping them in the magnetic trap, and retracting, right? And from here, we're basically doing the second stage cooling. And notice that number that you're seeing is amps, and it's 388 amps. That's a lot of amps. So there's that much current going, in those coils to suspend the atoms and do the cooling, right? All right, cool. So let's talk a little bit of math here. So basically, here in this little GIF that I'm showing the formation of a Bose-Einstein condensate of rubidium-87, right? So these are time steps, basically. Initially, you have a broad cloud of atoms, right? And you start the cooling process, and you notice that the peak becomes sharper and sharper as you make the cloud colder and colder. Basically, this peak tells you that all these atoms, almost all these atoms, are falling into the ground state of the system and basically are in the same quantum state. So mathematically, to describe, Bose-Einstein condensate, you have an equation called Gross-Perjevsky equation. It's kind of similar. It's kind of similar to Schrodinger's equation. If you didn't have this nonlinear term, right? You have the kinetic term, you have the potential term, and you have energy and the wave function of both sides, right? But because you have some interaction, you have these atoms that are interacting with each other, you don't have a linear system. You have to somehow count for the nonlinearity of the system. So what do people do with these BECs in their lab? There are hundreds of BEC labs since the discovery of BECs across the US and across the world. Um, what they do, so these BECs are like superfluids, right? You can simulate some very interesting physical systems that are very difficult to calculate or simulate, that basically can lead to, these researches can lead to the next generation of computers, quantum computers, um, or basically some communication devices in the future. So these are very, very important researches that people are doing. We are in the primary steps, but we are basically finding some really, really interesting things from these Bose-Einstein condensates. So I was going to say, what do we learn from these BECs basically? So there are several ways of manipulating the BEC and get some information from the system. You can manipulate the kinetical term, right? You can manipulate the potential. You can pour the superfluid into different containers and see how it forms and shapes and things like that. You can also play with the interaction between the atoms. It turns out if you can very carefully tune your magnetic field around your BEC, you can actually control the interaction between these atoms, and therefore you can control the nonlinearity in the system. And it's very neat. It leads to some really, really cool nonlinear superfluid states like solitons or a whole bunch of other phenomena that are really, really interesting to study. All right, so without I don't want to make this video too long, so I think we had a decent introduction to BECs. I'll see if I can put together another video to give you more information about Bose-Einstein condensates. But I think at this point we are at a decent point where we know a good amount of information about BECs. All right, so thanks for hanging out, and see you guys next time.